Okay, so we were talking about mixed strategy extensions of strategic form games, of actually finite strategic form games. The mixed extension, we only considered games where the strategy set of each player is finite. We didn't want to get into the technical details of probability measures when the strategy sets of the players was not finite. So I'll write down one fact that we wrote the last time we studied mixed extension games, which was the following: for any mixed strategy profile, and the expected payoff of player I from the mixed strategy profile mu was the convex combination of, let me write it first and then. Okay. So the expected payoff of player I from the mixed strategy profile mu was a convex combination of the expected payoffs that he would get when he plays the pure strategy SI, given that the other players play the according to their mixed strategy under mu. Okay, just a very simple fact, but we'll keep making use of that. Actually, last time we talked about these, we wrote the proposition, which we didn't give the proof. Today we'll do the proof. And we'll use this heavily. So what we had was, for any player I, for any mixed strategy profile of the other players, and for any mixed strategy of player I, what we had was the mixed strategy mu I was the best response of player I to the strategy profile mu minus I, if and only if the support of mu I was a subset of the best responses of player I to the strategy profile mu minus I. Okay? Recall, let me remind you what this was. This is the set of all strategies of player I, which are played with a positive probability under mu I. Okay? So let's prove it. That's a if and only if statement. Sometimes when we're lucky in one step, we can prove the if and only if statements, but most of the time we usually first prove one direction and then the other direction. Okay, which one do you want to start with? Oh, let's start with. Okay, so what do we want to show? It's always a good idea to write down what you want to show. When I was taking classes from Semih Koray, when he did proofs, he would stop and write what we want to show. What we want to show is if mu I is a best response of player I to mu minus I, then then, well, let me write that a little bit explicitly. Then for any SI in the support of mu I, SI is a best response of player I to mu minus I. Again, as I said before, we're abusing language. And when we say SI, this is actually a subset. If you remember, we're talking about the mixed extension game. This is a subset of delta S minus I, SI. So it's a set of mixed strategies. But we said every pure strategy can be represented with a mixed strategy. So we're abusing language. So that's what we want. So this is what we want to show. Okay. So let's take an arbitrary element. Take an arbitrary strategy profile of the agents other than agent I, and mu I in delta SI be such that mu I is a best response of player I to mu minus I. So, bless you. This is what we want to show. Bless you. So, what do you do? So again, sometimes it's a good idea to write intermediate steps of what you want to show. So right now, what do we want to show? Show that SI, which is in the support, is a best response. So what we want to show that for any SI in the support of mu I, we have UI, no, capital UI, the expected payoff from playing SI when the other agents play mu minus I is greater or equal to the expected payoff from playing a strategy profile mu I prime, given that the other players are playing mu minus I. And, okay, make sure that everything checks out. Everything should be quantified. SI comes from here. Mu minus I was given here. Where did mu I prime come? So we should add that quantifier. And this is true for any mu I prime in delta SI. So this is what we want to show. So this is what we want to show. Well, we'll do proof by contradiction. So far, so good? All clear? Okay. So assume that this is not the case. So let me call the star. Assume star is not true. Then what does that imply? That implies that there exists an SI in the support of mu I. There exists a mixed strategy of player I, mu I prime, such that the expected payoff from playing mu I prime when the other players play according to mu minus I is greater than the expected payoff from playing SI when the other players play mu minus I. So what? What does this imply? Sorry? Mu I prime is the best response to mu minus I. Everybody agree? Does everybody agree? Not necessarily, right? It's maybe there is a mu I double prime, which even yields a larger expected payoff. So just because this holds doesn't mean that mu I prime is the best response to mu minus I. Okay? But it means that SI is not a best response, but that's what we assumed already. So what would that imply? Now, what do we know about this expected payoff? It's a convex combination, so write this thing with primes. Okay, so it's a convex combination of his expected payoffs. Okay, when he plays the pure strategies SI, given that the other players play according to mu minus I. Okay, so that number is actually, well, we have some similarity there. Okay, so actually, this term is also in this summation. Okay, so if this expected payoff is greater than that, what does that imply about this sum? What would that imply about that sum? Any ideas? By the way, I've realized that last week, because preparing the exam, I realized that actually I talk too fast. I give up answers too early. Normally, I don't do that. I wait patiently for somebody to come up with an idea. So I'll go back to my old teaching method. I'll just wait for somebody to answer. So what does that imply? That's what we have. So it's a very simple fact, but it's very useful. Okay, and what does that say? The convex combination. Convex combination because the sum of the coefficients have to add up to 1, and the coefficients are all non-negative. Because of that, this expected payoff is always less than or equal to the maximum of these numbers, and greater or equal to the minimum of these numbers. So, what does this imply?
There must be another SI, right? Which has a higher expected utility. Otherwise, it will be greater than this.
Exactly right. If every term here was less than or equal to this term, so actually, let me change. We have an SI here and an SI here, but this SI is a dummy variable. This SI is the fixed variable that we're given here. Or actually, let me change this. I'm sorry. Let me put a prime here. Prime here. Okay. So if all these terms was less than or equal to this term, the convex combination would be less than this term. Okay? So, which means that if this holds, if that holds, so this implies that there exists an SI double prime in capital SI, but not in only capital SI. It has to be in the support of mu I prime. Otherwise, its weight would be 0, and it will not show up in the summation. So actually, there exists an SI double prime in the support of mu I prime. That's what we're looking at. Such that the expected payoff from playing SI double prime when the other players play according to mu minus I is greater than the expected payoff that the agent I would get when he plays SI prime, given that the other players play according to mu minus I. So what? Well, what are we doing? We're doing proof by contradiction, right? So this was what we wanted to show. So we assume that it's false. So we want to arrive to a contradiction. What can we contradict in this set of arguments? What can we contradict in this set of arguments? Sorry? Which inequality? This one? Well, we already assumed that this is false. So our assumption is false. You mean that this statement is true? That's one thing. But if we could show that this is true, then we wouldn't have to use proof by contradiction, right? We would have directly obtained this. Yep. So certain things we took SI to be in the support of mu I. We could show that that's false. What else? Well, let's think simple. If you're doing we're having a statement of the following: P implies Q. In proof by contradiction, you assume Q is false. And what do you try to get to? You try to contradict P, right? In our case, what was P? That was right. Remember, the statement was, if mu I is the best response of player I to mu minus I, then we're trying to prove this side, then this holds, which was equivalent to this, which was equivalent to this, okay? So, well, maybe we should get a contradiction to this statement. How do you contradict this statement? There's some mu I prime, there's some mixed strategy of player I, which, well, you show that mu I is not a best response. How do you show that mu I is not a best response? You do what your friend did. Find a mixed strategy which yields a higher expected payoff than the expected payoff yielded by mu I when the opponents play mu minus I. So, does anybody have an idea about what that mixed strategy should look like? So what do we know about mu I? Mu I is the best response to mu minus I. SI, mu I is such that SI is in the support of mu I. That is, SI is played with a positive probability under mu I. And SI prime, So SI prime is in the support of mu I. And SI double prime is in the support of mu I prime. And what happens? SI double prime yields a higher expected payoff than SI prime does when the opponents play mu minus I, which is always fixed. Yep.
Can we take mu I prime to be mixed strategy so that SI double prime is always played?
So you mean we're defining a new mixed strategy. So we're thinking, so maybe it might be wrong, don't rush in writing. We're looking for another new mixed strategy. So we used mu prime, so let's call that mu I double prime. So you want this mu I double prime to be such that mu I double prime SI double prime is equal to 1. And hence, mu I double prime SI is equal to 0 for any SI different than SI double prime. Okay? Is that what you want? Will that work? Will that work? Yes, sir.
I think instead we should take all the problems from psi prime and put it into a psi.
So your friend said, well, this has, because it's in the support of mu I, under mu I it's played with some positive probability. So you want to take it from here, put it there.
Not necessarily. Psi double prime does not become one necessarily.
The psi?
There might be other strategy, other problems. So
Exactly.
double prime does not become one.
Well, yeah, actually, when you do that, maybe you're getting even a lower expected payoff. Okay? So, so this only compares these two. We don't know how this number is compared with this number when SI is different than SI prime. So maybe sometimes it's like this. And then when you put all the weight, you'll get a smaller expected payoff. Okay? But what your friend said, so you have two strategy profiles, and when your opponent's strategy profile, mixed strategy, is fixed, playing SI prime yields a higher expected payoff than playing SI. Then what would you do? Would you play SI prime? No, you would shift all the probabilities to something which yields higher expected payoff. So, define double prime as follows. Mu I double prime SI is equal to mu I SI prime plus mu I SI double prime if SI is equal to SI double prime. Okay. 0 if SI is equal to SI prime. Okay. So previously, SI prime was played with this probability, a positive number. Now I'm shifting all that probability to SI double prime. And then don't change anything else. If, well, otherwise. Okay. So very simple idea. If something does better, play it more frequently. Okay? So we claim that the expected payoff of player I by playing mu I double prime is greater than the expected payoff that he gets by playing mu I, given that the opponents play according to mu minus I. Okay? So let's write that. Okay. Just by definition. So what is that equal to? Well, that's equal to, well, let me write it the short way. SI is not an element of SI prime, SI double prime. Okay. Well, if SI is not equal to SI prime or SI double prime, this term becomes equal to mu I SI. Plus, when SI is equal to SI prime, mu I double prime SI prime is equal to 0, so that will not show up in the summation. And when SI is equal to SI double prime, mu I double prime SI double prime is equal to this term. So what we have is So actually, if we put these two together, what we get is summation SI different than SI prime, mu I SI times capital UI SI mu minus I plus mu I SI prime times UI SI double prime mu minus I. Okay? So the problem we have is the strategy here and the strategy here are different. Okay? This strategy and this strategy is different. If they were the same, I would have just said this is the expected utility of player I when he plays mu I and the opponents play mu I minus prime. So if these two were the same strategies, I would have just said, let me write that better. I would have just said this is equal to the expected payoff that player I would get when he plays mu I and the opponents play mu minus I, okay? Which would be a contradiction. Why? Why? Because we had this, okay? Because of that, that would yield a contradiction. But that's not equal to that. So what to do? What to do? Again, what was the purpose? The purpose was to show that mu I is not a best response. That is, there is a strategy of player I, in which case we hope that it's mu I double prime, which yields a higher expected payoff than mu I does. So on one side, I need the expected payoff that player I gets from mu I double prime. On the other side, I need the expected payoff that player I gets when he plays mu I, given that the other players play mu minus I. But this is what I want. This is where I want to get. I don't need equality in between, okay? This is where I want to get. This is what I have. What to do? Yeah, we're trying to, so again, what was the purpose? What? Okay, at this stage, we want to show that, we want to arrive to a contradiction, and we decided that we can arrive to the contradiction if this expected payoff is greater than this expected payoff. Okay, so I want to be able to compare this with this. We know that this is equal to this animal, which is very close to this, but not equal to this.
So we can write UI SI, or rather we can subtract and add UI SI prime mu minus I to that.
Wait a minute. Add and subtract what?
UI SI prime mu minus I.
Add and subtract.
2 greater than 0.
Which is greater than 0. Exactly. But you can even do it so your friend, you see, the trick your friend does, which is a trick that we do and use in mathematics very frequently, you see, in order to get this, we need a prime here. Okay? So what your friend did was added this term and then subtracted the same thing. Added 0. Adding 0 doesn't change anything. But there are many ways to write 0. He preferred to write it like that. Okay? Then what he did was change the terms. So he got this plus this is that. But then there's an extra term. And he showed that the extra term is positive, which we're almost done. But we could have done the same thing with even easier way, right? Well, we know that this number is bigger than this number. So if we replace this term with this term, what do we get? we get right? So what do? We took this term, replaced it with something smaller. As a result, you get something smaller, provided that what? Equal to 0, right? If this term is equal to 0, then replacing this term with something smaller doesn't change anything. Okay? But what do we know about mu I Si prime? We already know that Si prime is in the support of mu I. So we know that mu I of Si prime is different than 0 and this term. So the fact that Si prime is in the support of mu I together with this implies this statement. Okay? But this is exactly equal to the expected utility player I gets from playing mu I, given that the other players played according to mu minus I, which is a contradiction for mu I being, So this expected payoff is greater than this expected payoff, which contradicts with mu I being a best response to mu minus I. That's it. Okay. So by the way, here, I don't need this to be positive. It could be 0, it could be positive. What matters is this being positive, because that's what we used. Okay? So far, so good? So far, so good? Just simple algebra. And essentially uses this very simple fact. Nothing fancy. Well, we needed some creativity here. Okay? Any questions? So, 1 down, 1 to go. We proved that the left-hand side implies the right-hand side. Now what we have to do is prove that the left-hand side, the right-hand side implies the left-hand side, which is actually easier. Should we do it, or can I leave it as an exercise to you, or? Let's do it. Okay. Okay, so this time we want to show the other direction. So what we do is let I be a player, mu minus I, a strategy profile of all the agents, a mixed strategy profile of all the agents other than agent I, and mu I, a mixed strategy of player I, be such that support of mu I is a subset of the best response says of player I to mu minus I. Okay. So what do we want to show? Want to show that mu I is the best response of player I to mu minus I. Yeah, and it's always a good idea to write down where you want to arrive. I learned many things from Simoja. This was one of the things that made my life easy when I'm doing proofs. If you don't know where you're going, where you want to get, it's very hard getting there. Okay, so what do you do? Well, first, let's write down what this means. Okay, let's simplify this. Okay, so support, well, actually, let me write it even simpler. I of SI is different than 0. Well, if it's different than 0, it has to be greater than 0. Then the expected payoff of player I from playing SI, given that his opponents play according to mu minus I, is greater or equal to the expected payoff that he gets by playing mu I prime, given that his opponents play according to mu minus I. And what is the quantifier on mu I prime? What is the quantifier on mu I prime? So we're saying that SI is a best response to mu minus I. So it should be greater or equal to for all. So don't forget to quantify them. That's what we want. So this is what we have. Again, let's write down what we want to show. Okay? So when you're doing proofs, you start from here, you want to get to here. Sometimes you move forward. You say, from what I have, I can get this. That's what we had. From this, we have this. This is where we want to get. Sometimes it's a good idea to backtrack a little bit. Okay, so to come here, you have to arrive here. So let's expand this a little bit more. So what do we want to show? Well, what does that mean? It means that for any mu I prime and delta SI, for any mixed strategy of player I, the expected utility that he gets from playing mu I, given mu minus I, is greater or equal to the expected utility that he would get by playing mu I prime, given that his opponent plays mu minus I. Okay? So this is where we want to get. If we get there, we will be here. We will be able to get here, which is what we want to show. Okay? We started from here. We arrived there. So we started here. We came here. This is where we want to go. But if we come here, we'll be able to go there. Now, look at what we have and look at where we want to get. Look for the similarities. Okay. But then there's also some difference. Here we have expected payoff from pure strategies. Here we have expected payoff from mixed strategies. So the right-hand sides look good. The left-hand sides are different. So if I can convert this into this, we'll be done. Can we do that? Yes, sir. Well, let's give everybody a minute to think. In the meantime, it's always good to think writing. So whatever comes to your mind, just take a minute, write it down. Again, one of the useful things that I learned from Semyoja was that, writing is a way to organize your thought, and organizing thought is an important step in learning. So don't be lazy. Write down what you have in your mind. Think. This is where we are. This is where we want to get. Look at the similarities between where you are and where you want to get to. Look at differences. and think about how you can play with the differences to get where you want to. Yes, sir.
Since we know that SI is a best response to expected utility of mu I prime mu minus I.
Wait, come here. SI is the best response to of player I to mu minus I, yes.
Hence, SI is the maximizer of the expected utility function of mu I prime, mu minus I for any mu I prime.
Yes, that's what we already wrote down.
But now, since for any support, for any SI that we have in the support of mu I,
Uh-huh.
we know that the expected utility function of all strategies in that support are the same.
We know that the expected utility from all the strategies in the support
Are
are, well, if two strategies are best responses, okay,
the same expected utility function.
they will yield the same expected payoff, okay.
Now,
So what?
we know that the expected utility of mu minus I is a convex combination of the expected utilities of that.
Uh-huh,
But since they are all the same,
uh-huh.
it means that a convex
The-
combination of the same things will yield the same.
Okay, well, very good. Except it needs a little brushing. Well, not all expected utilities are the same. There are, when you take the convex combination, you don't take the convex combination only of the,
Yeah, but the probabilities of the other strategies are zero.
are zero, exactly. So you don't really care about them, okay? So, did you see what your friend did? Okay, so if there are two strategies in the support, because they're both best responses to the same strategy profile of the opponents, they will have to be equal. So when you're taking this summation, any term which has a positive probability will have the same expected payoff. Okay? But what would that yield? Okay, if you're taking the average, the convex combination is nothing but a weighted average. If you're taking an average of the same number, the average will be equal to, if you're taking the average of 5 and 5 and 5 and 5, the average will be 5. Okay? So if all these terms are the same, their average will also be the same. So actually, your friend says that ui of mu will be equal to this number, which is greater than that. And that completes the proof. Okay? Or, again, we can write it a little differently. Because this is true, I can multiply both sides by mu I of Si. Since, let me write that bigger. It might not show up on the, let me erase this top part. So multiply the left-hand side and the right-hand side with mu I and Si. Because this number is non-negative, the direction of the inequality will not change. Okay? So I'm going to do the same thing that your friend did in a little different way. Okay? So I'm multiplying both sides with yeah. I should keep that. No. Let's try to finish. So we have so we had that. Let me sorry, I'm rushing because I don't want to take up your break. Okay, so we have this. Take the summation over all Si. Okay, well, this doesn't depend on Si. So when you sum these up, okay, you will get okay, on the left-hand side, you will get this. On the right-hand side, you will get this. On the left-hand side, you will get that, which actually concludes that UI is the best response. The last part I went fast, but your friend had the idea. I think I like that quite a bit. It just relies on the simple fact that the expected payoff is a weighted average of the expected payoffs from pure strategies. Okay? And if they all yield the same number, the average will be the same thing. Okay? Any questions? Let's take a break. Sorry, I went over time a couple of minutes.